Every time it rains over Europe today, something else comes down with the water that simply wasn't there a few decades ago. It's a tiny man-made chemical called TFA, trifluoroacetic acid, part of the wider PFAS forever chemical family. Scientists are now finding it in rain, rivers, groundwater, and even drinking water. And here's the twist. A big part of this pollution doesn't start in a factory chimney. It starts in equipment that is marketed as green: air conditioners, heat pumps, and refrigeration systems filled with low-GWP, fluorinated refrigerants. In this video, I'll explain how some of these climate-friendly refrigerants break down into TFA, why that's a long-term problem for our water, and what safer alternatives we already have. To understand TFA, we need a quick tour through the history of refrigerants. First generation, CFCs and HCFCs. Fantastic technical performance, but terrible for the ozone layer and the climate. That led to the Montreal Protocol and a global phase-out. Second generation, HFCs. They solved the ozone problem, but many of them still had very high global warming potential, GWPs in the thousands. Third and fourth generation, HFOs and hydrogen hypofluorite-based blends. They were designed specifically with low GWP in mind. On paper, it looks like the perfect success story. We keep our comfort and cold chains, and the climate impact drops dramatically. But that's only half of the picture. Let's talk about GWP, because it's at the center of the marketing around these gases. GWP, or global warming potential, tells us how strongly a gas warms the atmosphere over a defined time period compared to carbon dioxide. It's an important metric, but it only tells one story: climate impact. What GWP doesn't tell us is what happens when the molecule breaks apart in the atmosphere. It doesn't tell us whether the breakdown products are toxic, or whether they persist in the environment for decades or centuries. So a refrigerant can have a very low GWP and still create serious long-term pollution once it degrades. This is exactly what happens with certain HFCs and many of the modern HFOs. When these refrigerants leak into the atmosphere, and we all know leaks happen in real systems, they don't stay intact forever. Sunlight and other chemical reactions break them down. For several of these gases, a large share of the carbon and fluorine ends up as TFA, trifluoroacetic acid. That TFA is then washed out of the atmosphere by rain and snow and deposited onto soils, into rivers and lakes, and ultimately into groundwater and drinking water. So, a low GWP refrigerant can still be feeding a long-term PFAS problem through this invisible pathway. So what is TFA in simple terms? Chemically, TFA is a very small organic acid with 3 fluorine atoms attached. Those carbon-fluorine bonds are extremely strong, which makes the molecule very resistant to breakdown. That's why TFA is considered very persistent. Once we create it, natural processes struggle to remove it again. On top of that, TFA is highly soluble in water. That makes it very mobile. It happily travels with rainwater, river water, and groundwater. Put those two things together, persistence and mobility, and you have exactly the kind of chemical that tends to spread globally and accumulate in water systems over time. You've probably heard of PFAS, the so-called forever chemicals, used in non-stick coatings, firefighting foams, textiles, and many other applications. TFA belongs to the same PFAS family, but it's an ultra-short chain member. It behaves a bit differently from the long-chain PFAS that have been in the headlines, but it shares two important features. It is very stable, and it is very hard to remove from water once it's there. That's why more and more researchers and regulators are starting to look at TFA not just as a curiosity of atmospheric chemistry, but as a serious environmental contaminant in its own right. Once TFA is formed, it basically joins the global water cycle. It's carried in clouds and rain, deposited on land and into rivers, seeps into soils and aquifers, and passes through water treatment systems. Conventional drinking water treatment is not designed with TFA in mind. Because it's so small and so soluble, most standard treatment steps don't remove it efficiently. That means a portion of the TFA that starts life as a leaked refrigerant molecule can, in the end, arrive at your kitchen tap or in bottled mineral water. And unlike carbon dioxide emissions, which at least dilute in the atmosphere, TFA is concentrating in something far more precious and limited, our freshwater. So how big is the problem right now? Monitoring campaigns across Europe have started analyzing rainwater, rivers, groundwater, and drinking water for TFA. The picture that's emerging is quite clear. TFA is now found in a large share of samples. Concentrations in some regions are increasing over time. In many cases, the measured values are still below health-based guideline levels. That's important to say. But we're talking about a pollutant that is being continuously generated and that we don't have an easy way to remove once it's in the environment. So the key question becomes, do we want our refrigerant choices to be a major ongoing source of a persistent PFAS in water? Modeling studies look at what happens if we fully follow the current path, phasing down traditional HFCs and replacing them mostly with HFOs and hydrogen hypofluorite-based blends. The result is straightforward. As the stock of HFO-filled equipment grows, so does the annual formation of TFA in the atmosphere. The models differ in the exact numbers, but they agree on the direction. We lock in significantly higher TFA loads in surface waters and groundwater for decades to come if we fully commit to fluorinated low-GWP refrigerants. Once that TFA is out there, there is no realistic way to clean it all up on a global scale. So prevention, avoiding the formation of TFA in the first place, becomes the logical option. One thing that often gets overlooked in this debate is scale. We're not talking about a handful of experimental systems. We're talking about millions of air conditioners, heat pumps, supermarket systems, and industrial plants worldwide that are being filled with fluorinated refrigerants. Even with good practice, there are always losses, during installation, during operation, and at end of life. Each of those leaks is small on its own, but together they add up to a continuous flow of fluorinated molecules into the atmosphere, and, eventually, into TFA. That's why this is not just a theoretical laboratory issue. It's a real-world, system-level problem tied directly to the refrigerant choices we make. So what are our options? On one side, we have PFAS-based F-gases, many HFCs and HFOs. They offer low GWP, but at the cost of creating TFA and other persistent breakdown products. On the other side, we have natural refrigerants, carbon dioxide, ammonia, hydrocarbons like propane and propene, as well as water and air. These substances are part of existing natural cycles. They have their own challenges in terms of pressure, flammability, or toxicity, but they do not create new persistent PFAS when they leak. From a long-term environmental perspective, that's a fundamental difference. At this point, people often say, yes, natural refrigerants sound nice, but they're dangerous or too complicated. It's true that they are not drop-in replacements. Propane is flammable. Ammonia is toxic. CO2 runs at high pressure. But the safety and complexity issues are engineering challenges, not fundamental showstoppers. With correct system design, proper components, standards, and training, we already have thousands of safe, efficient natural refrigerant installations running every day. The real barrier is often familiarity and regulation, not physics. If we're serious about protecting both the climate and our water, it makes sense to invest that engineering effort into natural refrigerant solutions rather than into yet another generation of fluorinated PFAS molecules. Whether you're a manufacturer, a planner, an installer, or a building owner, you can already start making better choices just by asking a few extra questions. Don't stop at, what's the GWP? Also ask, is this refrigerant a PFAS? Does it break down into TFA or similar persistent substances? Are there technically feasible natural refrigerant options for this application? Simply bringing these questions into the conversation shifts the focus from short-term compliance to long-term responsibility. Let's wrap this up. Low GWP fluorinated refrigerants were an important step forward compared to older high GWP HFCs, but they are not the end of the story. If we focus only on GWP and ignore TFA and the wider PFAS issue, we risk solving one environmental problem while quietly creating another, this time in our water. The good news is that we don't have to accept that trade-off. Natural refrigerants offer a proven path to efficient, reliable cooling and heating without adding new, forever chemicals to the environment. So the takeaway is simple. Don't stop at the GWP number. Ask what a refrigerant turns into when it leaks. And whenever possible, choose solutions that are both climate-friendly and PFAS-free. Thanks for watching. If this video changed the way you think about refrigerants, leave a comment below. I'd be especially interested to hear, should breakdown products like TFA be considered when we define green refrigerants?